Welcome, everyone, to tonight's session on radical reactions. Tonight's session is going to cover the basics and stability, the arrows, the steps of a radical reaction, initiation, propagation, termination, and a fun trick there, radical halogenation for alkanes, alkenes, and allylic halogenation. If you are here and you're wondering if this session is for you, tonight's session is at the undergraduate level. So if you're taking this class in undergrad, or if you're reviewing these concepts for an exam like the MCAT, PCAT, DAT, or similar, then you are in the right place. In addition to tonight's session, I also created a practice worksheet, which you can get after the session by going to the link on the screen, leahforsci.com/orgolive, where you'll get a link to the recording, the practice worksheet, and the notes from tonight's session. Let's begin with the concept of a radical. Most of chemistry, anytime you're looking at reactions, you tend to look at electrons in pairs because electrons prefer not to be alone. They prefer to be paired up, and that makes them happy. That makes them stable. If an electron is by itself, meaning you somehow manage to break it away and you get molecule A with a single unpaired electron, this is going to be very, very unstable. If you recognize from my other videos what happens when something is unstable, well, let's do the reverse of that. If something is happy, it will be stable. And if it is stable, it is unreactive. It is not looking to change its condition. It's not looking to change its situation. That means if something is unhappy, then it is unstable, and that makes it very reactive, which is exactly the case for radicals. That's why if you hear about free radicals are dangerous and free radicals are bad for you, because they're so unstable, they're going to start attacking everything in your body, in your cells. They're looking for a mate, they're looking for a pair. Given that they are unstable, there are different levels of instability, and the radical stability you should recognize as very similar to carbocation stability. The more substituted the radical, the more stable it's going to be within the realm of unstable. And that means if you have a radical by itself, just a methyl radical, this is the least stable that you can get. Slightly more stable will be a primary radical. That means a radical sitting on a primary carbon. Slightly more stable than that will be a secondary radical, a radical sitting on a secondary carbon. And more stable than that is a tertiary radical, where the radical sits on a tertiary carbon. For the regular straight chains, or branch chains, or rings, or anything like that, this is the order of stability where the tertiary radical is going to be the most stable. But just like with carbocation stability, one other way to stabilize a radical is if the radical can be shared by more than one atom. How do you share the burden of a radical with more than one atom? Resonance. Resonance is how you share a burden of charge, and in this case, the burden of a radical. If I have a radical on a primary carbon, but there's a pi bond next to it, the resonance structure will distribute that pi bond to the right, putting the radical on the left. And that means this radical is being held by two different carbons, making it even more stable. And if I could have more than one pi bond to resonate, more than one pi bond to share, for example, if I have a benzene ring with a radical sitting outside the ring, this is going to be even more stable because I can resonate this radical into the ring, and that means I'm sharing it with four atoms, and that makes it even more stable. Question: is this different from curved arrows to indicate movement of electrons? Yes and no. That is a very, very good question, because when you're looking at arrows, in the typical reaction, if you have A bound to B and it breaks apart to give you A now having 2 electrons and B having no electrons. The way that you show this is the bond collapsing, in this case, onto A, and you show it with a double-headed arrow like this. I like to think of this double-headed arrow where the hook has 2 tips, one for each electron that is moving, because notice they both move together. This is considered heterolytic cleavage, where hetero means different, lytic means to break, and cleavage is just a redundant term there. Heterolytic cleavage meaning the bond breaks where the 2 electrons go to it's an uneven separation where one gets 2 and one gets nothing. But if you have a radical reaction, then the way this splits up is going to be different. If I have a molecule where A is bound to B, and once again there are 2 electrons between them, but this time I break it up so that A gets 1 electron and B gets 1 electron. These are 2 radicals that I just formed. This is called homolytic cleavage, where homo means the same, lytic is to break, and cleavage again is a redundant word. Homolytic cleavage, you show this with an arrow that has just 1 tip. So the arrow tip, I imagine that the 1 tip, that fish hook, is representing 1 electron. But if I have the double, then that's representing 2 electrons. Alia, that was a very good question. I hope that makes sense. And then going back to resonance, if I want to show what is happening here, we'll show this electron in purple with a fish hook here, this electron in blue with a fish hook here. That gives me the blue electron as a radical, the purple electron now sitting with the green electron, which also shows a fish hook because they're coming together. And that is how you show the radical resonance, where each arrow only has 1 tip, that 1 fish hook, to show that it's a radical rather than a pair of electrons. If you're with me so far, give me a thumbs up in the comments, because we are about to go into reactions and I want to make sure that you're with me, that we're all on the same page. Starting with the 3 steps to a radical reaction. A radical reaction, not the mechanism that you're going to see, but rather the 3 types of steps that you are going to see are as follows. And I'll explain the difference afterwards. Step 1 is initiation. If you think about the word initiation, it implies to initiate, to begin. Initiation is how we create a radical from a situation where we don't have a radical to begin with. Using our A bound to B example, and I'll show you specific examples once we get into the mechanism. If I have A bound to B, and I show you actually what I showed you before, where they break apart like this, 2 half arrows, my product will be A radical and B radical. Initiation is when I have no radical creating a radical. So this is when I form a radical, or form radicals, technically 2. And this is the first step that you're going to see in the mechanism for a radical reaction, because without it, you don't have a radical to react. The second step is propagation. What do you think of when you hear the word propagation? You should be thinking of to propagate, meaning a chain reaction, something that continues. And this is what happens when one radical attacks a non-radical to give you another radical. So let's show what that looks like. If I have radical B from the last step, and it comes upon molecules C and D, radical B will attack C. C will donate one of its electrons so it can form a bond, and D will break away. This now gives me, well, we had B, C, and D. B had a blue electron, C had a green electron, which is now bound to the blue one. D had a purple electron, which is now sitting by itself. Propagation is a chain reaction. And this is when we propagate. We take a radical, we attack something, we make another radical. Jada says to repeat over and over. Exactly. We just keep making radical after radical after radical in the same, basically a repetitive step over and over. The last step, and this is the least common, which I'll show you when we do the mechanism, is called termination. Termination, as the name implies, is to terminate, to finish. A termination reaction is when you have two radicals. So let's see what we had above. We had radical B just hanging out, radical D just hanging out, and the two radicals come together. So we have a fishhook here, a fishhook here. So that's two lone electrons coming together to form a bond, and the radical is gone. The termination step is the finish step. It's not finishing a reaction, it's finishing off the radical. No more radical. That's key to recognizing for later. Professors typically like to ask, do this entire mechanism and then label each step as initiation, propagation, or termination. Sometimes, especially students taking the ACS, and let me know in the comments if you're taking the ACS exam, you will be given one step in a big mechanism and you will be asked to label it initiation, propagation, termination. And here is where I'm going to show you a trick to recognize. In an initiation step, because you initiate, you should have no radicals on the left. That means the left, when you're starting out, is going to be 0, and the right equals 2. 2 radicals on the right because you're initiating from nothing to 2 radicals. If you're faced with a propagation step, the way you recognize it is in knowing that propagation is a chain reaction. And so a chain reaction is the same thing over and over and over and over. And that means whatever you have on the left, you should also have on the right. So the key with a chain reaction is one each, right and left. One radical on the left, one radical on the right. Step. And are we learning the alphabets? We're starting out simple, and then we'll do the step-by-step mechanism because first I want to make sure you understand the steps. So let me know in the comments if you're following me with the steps using the alphabet before we get into the specifics. And finally, for a termination step, because termination is to finish, is to kill it off, the key is that you start out with radicals and then you terminate, and so you have no more radicals. That means the left is 2 and the right is 0. If this is what you're asked for, don't worry about thinking of, oh wait, so which mechanism was this? Which reaction? Don't even worry about it. Look at your radicals. Are they on the right, the left, or both? And that is how you can quickly tell if it's initiation, propagation, or termination. Let me know if your professor asks questions like this, and if yes, if you like the trick. And then let's see if you're ready to put this into practice with the first mechanism, which we'll look at, and that is the radical halogenation of alkanes. And for this, I am going to use typically, not just me, you typically see for this chlorine and bromine, because fluorine and iodine are both no good for these reactions for 2 different reasons we're not going to go into. Just know that we're typically looking at Cl2 or Br2. So let's start with a very basic reaction. If I have a molecule of methane and I react it with Cl2, at room temperature, nothing is going to happen. But if I raise this to a high temperature, a temperature high enough to destroy a dihalide, to break it up and turn it into radicals, this is where we're going to get the hydrogen being replaced by a halogen. So for example, CH3Cl plus HCl, and we can put heat or light. You'll also see H nu which is one way of representing that you're hitting it with a wavelength. The reason this is such a good reaction to know is because when you're dealing with advanced synthesis, in fact, let me know in the comments if you are currently in Orgo 1, Orgo 2, or preparing for an exam. If you're dealing with advanced synthesis, your professor may give you a problem that looks like this. Starting with cyclohexane, do whatever you can using whatever reagents you need to come up with something that looks like this with a carboxylic acid. And you're looking at this and you're trying to think of all the reactions you learned, and you know, the carboxylic acid could have come from an alcohol that I oxidized. And that could have come from, say, a halogen that I did an SN2 reaction, replaced it with an OH. But in order to even go in this direction, you could have done so many different things here. But in order to go there, you need to have something on the molecule to react, to substitute, to replace, to attack. If you have nothing on the molecule, you are stuck until you get a halogen, because a halogen is your best leaving group and the best way to start a reaction. And so I call this the something from nothing reaction, because we're starting with nothing on the molecule, meaning nothing reactive, and we're turning it into something that I can then do more advanced synthesis. And so here, if I can get a halogen on there, then I know I can replace the halogen. I can substitute the halogen. I can eliminate the halogen. I can do so many different things once I have that halogen on there. So let's look at this reaction step by step. Let's actually look at the mechanism for this reaction. The first step is the initiation, and that is where I have the Cl2 and I zap it with a wavelength strong enough to break it apart. So heat or light is going to be key to starting this reaction. And what will happen is the electrons that are holding the two chlorines together will break apart and give me two radicals. Now that I have the radicals, and there are additional electrons, but I'm focusing just on the radical because that's the piece that we're reacting today. Now that I have a radical, this radical is very, very reactive, and it's going to look for something to attack. What is it going to attack? Well, typically a situation like this will have a lot of chlorine in solution, which we turn into radicals, and a lesser amount of whatever else we have. Unless we're trying to control outcomes, then we'll put very little chlorine and a whole lot more of this. But in this case, we'll show our methane molecule with an innocent hydrogen sitting on carbon, minding its own business, until chlorine comes along and says, I'm lonely, I need an electron, and it attacks hydrogen. Chlorine will need a second electron to complete that bond. So this is our propagation step. Hydrogen is forced to donate an electron so it can bond to chlorine. And that will leave this electron to collapse back onto carbon. The intermediate, what we get as a result of this step, is going to look like this. Carbon is now bound to 3 hydrogen atoms, and it also has that one, you know what, let me show it with incorrect geometry just so we can focus on the radical. What is the hybridization for this radical? Let me know in the comments. This molecule here, carbon with a radical, very, very unstable. Somewhere in solution, I also have the purple hydrogen that was stolen, bound to the green chlorine that did the attack, with the 2 electrons forming a bond. And you'll notice when I showed you the reaction here, I showed HCl, but often your professors are going to ignore this and assume that it's self-understood that you have HCl, but they don't necessarily ask for it or ask you to show it. The HCl just wanders off somewhere in solution. We don't care about it anymore. We're left with a radical that is, once again, very unstable. This radical is looking for something to attack, and it's going to look for the thing that is easiest to attack. Let me move this down so we have some room. In this case, that's going to be another Cl2 molecule. That means a Cl2 minding its own business is suddenly getting attacked by the methane radical, forced to donate one of its electrons so that it can form a bond, and kicking that electron off with the other chlorine. Don't forget, I'm not going to show lone pairs every time because these will take forever, but I want you to know that they're there. As a result, what do I have? I have a carbon bound to 3 hydrogens. It had the one gray electron that it used to attack the blue chlorine, forming a bond between carbon and chlorine. And then I also have this chlorine now hanging out in solution with its new radical. This chlorine is then going to attack something, which is going to attack something, which is going to attack something, and the reaction will keep going. So I want you to take a look at all the steps that happened here. The first step was a neutral, non-radical molecule that we broke apart. This is an initiation step. Once we had the radical, it attacked a molecule to give me a molecule and a radical. So that means this step right here, I'll put it over the arrow. So this step right here was initiation. This step was propagation. The next step is not going to be termination. Take a look. Radical attacking non-radical to give me radical and non-radical. That is just another propagation step. And when this chlorine is going to repeat the process here, that'll be propagation and propagation and propagation. In all the mechanisms that you work on, in all the reactions we're going to see for the topic of radicals, you will not see termination. There's no termination in these standard reactions. Why is there no termination if that is step 3 of a radical reaction? As a quick reminder, this session is being recorded. If you sign up at layetforpsi.com/orgolive, you'll get a link to the video, a copy of tonight's session notes, and a practice worksheet where you can do additional practice on radical reactions. Question: will the chlorine have a negative sign? No, and that is a very, very good question. If you look at how to find the formal charge, I teach this in my formal charge video to use the shortcut of should minus has. If I have a typical Cl ion off somewhere in solution, chlorine should have a total of 7 valence electrons. Directly around this one, I have 8 valence electrons. 7 minus 8 is equal to -1. This is a chloride anion, a negative ion. But if you look at a chlorine radical, the way we've been showing it today, we have a total of 7 electrons. Should have 7, has 7, 0. Radicals are very reactive, but not because they have a charge. They're not anions. They're reactive because they are unpaired lone electrons that want to be paired, even though they have no charge. So that is a really, really good question. Radicals are neutral, anions are negative. Going back to the termination and why there is no termination in these mechanisms is very simple. When I start out with a reaction, a small percentage of Cl2 will be hit with heat or light and separate. Radicals, because they're so unstable, are not going to form very quickly, and they're not looking to form radicals. Radicals are very, very unstable. Once we form a radical, if you think about what you have in solution, thousands and millions of molecules and a tiny fraction of radicals, you have that one radical looking for a molecule, which causes one radical to look for a molecule. But the chance of a radical finding another radical, that's going to be very, very low. Because there's so few of them, the radical is much more likely to bump into a non-radical. Sometimes, though, professors will ask for all the potential termination products. And what you do then is you simply ask yourself, what kind of radicals do I have? I have a chlorine radical, so I could have 2 Cls bumping into each other. I have a methane radical. I can have two of those bumping into each other, or I can have one of this and one of this. So my three options are this and itself, this and itself, or the two with each other. Let me show you, just in case you're asked. Termination options. In the above reaction, we had a Cl radical, we had a CH3 radical. So all the options that we can have are Cl radical plus Cl radical to give me Cl. Well, why am I putting a 2 there? I already drew it out. To give me Cl2. That's one option. Methane radical bumping into a methane radical to give me an ethane, a longer carbon chain. Again, very low likelihood, but it is an option, especially if your professor is asking for it. And of course, you can have a chlorine radical bumping into a methane radical. Not really going to happen, but it is an option to give you a completely different way to get your product of CH3Cl. Question. So we need to use the formal charge equation? No, I was simply showing you why the radical has no charge or how to calculate that it has no charge. I recommend knowing how to do formal charge, but not necessarily in this situation. You don't need it here. Question. The fishhook is half an arrow, and it means that one electron is moving instead of a pair. Yes, exactly. That's why everything is one electron at a time. These will each come together one at a time for the different termination reactions. Aliyah, you're asking really good questions today. I love your questions and definitely keep asking them because sometimes I don't necessarily think to teach something unless I see a question about it. So you're bringing up some very good points. With the reaction I showed you, that was a really, really short chain. CH4 only had one option. But what if I give you something that looks like this, and I react it with Br2 and heat? When it's shown like this, you won't have to show your HBr side product. You can just show the halogenation unless your professor asks for it. I can have a product where the radical is going to form on the central carbon, giving me a bromine here, or the radical forming on the terminal carbon to give me a bromine here. And the question is, which one is going to form? Which one do you have to know? And very importantly, why? Oops, I already showed that one. And the answer depends on two factors. One factor that we have to look at is radical stability. If this comes from a radical at the secondary position, that radical would have been more stable, making this one a major product. But the second thing is something we're not going to go into today, and that has to do with the energy of creating the radical and forming the intermediates. Some of you may be required to know the Hammond's postulate. In that case, I recommend studying it. I'm just going to give you the takeaway from it, and that is when it comes to whoops, why does it say I've been signed out? When it comes to forming the products, you have to look at the ratio of the stability between the primary, secondary, and tertiary. For bromination, that is really, really important. Primary is much less likely to form than secondary, which is much less likely to form than tertiary. And the ratios, I had to memorize them. A lot of my students don't, but just in case you have to memorize them, I'll give you the numbers here. It is, what is it, 1600 to 80 to 1. Wait, no, I have them backwards. The tertiary is most stable to 80 to 1. And what this is telling you is that if I have the option to form a tertiary brominated product, the ratio between tertiary and primary will be 1600 to 1. And so looking at the above, I don't have a tertiary option, but I do have a secondary. And the ratio of major to minor will be 80 major to 1 minor, meaning you're pretty much only getting the major product for bromination. Chlorination is a little bit less selective. And again, memorize this only if you have to, but the ratio is 5 to 4 to 1. So let me show you why this matters. If I have a molecule that looks like this, and I react it with Cl2 in the presence of heat or light, now I have the option of putting the chlorine on the tertiary position or the primary position. The ratio between tertiary to primary will be 5 to 1, which means you would expect a lot more tertiary, except look at how many hydrogens I have. I have 9 primary hydrogens and 1 tertiary hydrogen, right? Because remember that these are all, well, I should show them on the reactant. There are 3 hydrogens here. So when it comes to chlorination, it's really a numbers game because the ratio is so close. And that means your products are going to be all over the place. The reason this is important is if you're doing a mechanism or you're doing a synthesis and you need a halogen here so you can eliminate or substitute or whatever it is you're trying to do, turn it into a Grignard, don't use chlorine because you're probably going to get the wrong product. Use bromine because the chance of getting bromine tertiary is 1600 to 1, and therefore you're a lot more likely to get that product. If your professor does not require you to understand this, don't worry about a word I just said and only focus on the fact that major and minor has to do with the more stable radical, the major product. The less stable radical will give you the minor product. Let me know in the comments if your professor requires you to memorize this. We had to memorize these numbers, and then we had to do the math to actually show exactly what percentage of primary versus tertiary we would get. I did not like those questions, so hopefully you don't have to know them. Question. In the case of allylic, why is primary more preferred instead of secondary? A primary is not more preferred instead of secondary unless you're asking why a primary allylic is more preferred than secondary. And in that case, it looks something like this. If I have a radical here that's primary, it can resonate like this to give me another structure that helps share the burden of that radical that looks like this. So this is primary allylic, and it's stabilized by the fact that it has resonance. This primary allylic would then be more stable than just a secondary radical because there is no sharing of the burden, and therefore it's slightly more stable, but it's stuck holding that burden by itself. That's a very good question. Let me know if that helps. Rishav, that is awesome. Okay, so the next mechanism I want to look at is the radical halogenation of alkenes, which should look somewhat similar to the alkanes, but also very different. So let's make sure we clarify the difference. When you learned alkene reactions, you would have learned 2 different types of halogenation. You would have learned the dark reaction and the light reaction. What does that mean? And did your professor call it dark and light? Let me know in the comments. While you're typing that in, let me show you what it looks like. If I have an alkene and I react it with, say, HCl in a solvent like CCl4, this is considered the dark reaction, but you're not going to see this as often unless your professor is trying to confuse you or differentiate. The product is going to put the chlorine on the more substituted carbon. Let's change the colors so you can follow the atoms. The chlorine will go on the more substituted carbon and hydrogen less substituted. But if I take this reaction and I do the same kind of situation, I react it with HBr, but this time I change my solvent, or I don't even have to show a solvent. I can just show light to show a light reaction. My product is going to be flipped. The bromine goes on the less substituted carbon, and hydrogen goes on the more substituted carbon. The first one follows Markovnikov's rule, so it's considered a Markovnikov product. And the second one is an anti-Markovnikov product. The dark and light is what tells us, very simply, do I have a carbocation intermediate or do I have a radical intermediate? If you go back to my halogenation videos, I explained that the mechanism puts a carbocation on the more substituted carbon, and then the halogen comes into attack. The same concept for why we have the regioselectivity this way is going to apply, except the stability is going to put the radical on the terminal carbon, and that is what I want to make sure you're very comfortable with. So let's look at this mechanism step by step. I put light, but we can also show peroxides. Typically, you'll see this with peroxides, but it's called the light reaction, and that's why I put light there as well. Just like with the first reaction, we have to start with an initiation step. So let's show our peroxides as a CH3OO CH3. And the absolute first thing I want you to recognize is the fact that I have an oxygen bound to an oxygen. This is a very, very, very unstable reaction. Unstable molecule. And the moment it gets hit with a little bit of high energy, it is going to break apart in a radical reaction. This is why if you think of hydrogen peroxide in your medicine cabinet, rubbing alcohol is a disinfectant. It's in a clear plastic bottle. Hydrogen peroxide is also a disinfectant, but it's kept in a very dark, thick bottle. Have you ever thought about that? It's in a dark bottle because we're making sure light doesn't hit it. Because if light hits it, we're breaking everything apart and forming a whole lot of radicals, which you don't really want in your disinfectant. This is going to give me 2 CH3O radicals. And don't forget these bonds, these electrons here. I'm showing the radical in bigger. It's the same size and type of electron. I'm just showing it in bigger to make it stand out. I have 2 radicals from something that had no radicals to begin with. That means this is an initiation step. And now that I have a radical, the radical is going to attack my HBr. So let's show the HBr over here, hanging out in solution, minding its own business when the radical comes along and says, hey, I need a partner. And hydrogen is forced to donate an electron so it can form a bond, which makes the bromine keep that leftover radical and break away in solution. This is going to give me, let's move this like this. Somewhere off in solution, I now have my CH3O bound to the hydrogen. I formed an alcohol. It floats away. We don't care about it. What I do care about is the fact that I now have a bromine by itself with a radical. And this bromine is very, very unstable. So unstable that when it happens to come across the molecule with a pi bond, it will attack the pi bond because it wants to not be alone. It wants a pair. Now, when it attacks the pi bond, the question is, does it attack here or does it attack here? And the answer comes not from understanding where bromine attacks, but rather from understanding what else happens to the rest of the molecule. So let me show you the 2 outcomes first, then I'll show you the arrow. Option 1 and option 2. If bromine attacks at the primary carbon, then I have the blue electron, which will show now bound with the red electron over here, and a radical forming at the secondary position. If bromine attacks at the secondary carbon, we'll show our blue electron with a red electron. And now a radical having formed, let's show the radical in a different color so we can tell the electrons apart. The radical having formed at the primary position. This intermediate is how you know where it's going to form. Which one is more stable? The secondary is more substituted. That makes it more stable. The primary is less substituted. That makes it less stable. And that means this is not what we're going to see because we need to form the most stable of the unstable potential intermediates. To show the bromine forming, to show that secondary radical forming, we have to show the bromine attacking at the primary position. Bromine will reach out to this carbon, one fish hook. We'll show this electron in red coming to meet it. We'll show this electron in blue collapsing and breaking away, giving me this as my intermediate. Since this is not my intermediate, we'll shrink it down and get rid of it, just as something on the side for you to recognize. And look at what happened. I had a radical, attacked a non-radical, which gave me a radical and a non-radical. That was a propagation step. And when this attacked, it gave me another radical. That means this was also a propagation step, but we're not done because we have to get rid of that radical. Well, luckily, there's more HBr in solution. And so we'll show the radical reaching for hydrogen. This hydrogen giving an electron to come and meet it. And bromine is forced to take that lone electron off somewhere in solution. This gives me my final product as follows. I have my carbon chain with this bond that we saw forming earlier, having bromine on the terminal carbon. We now have the light blue forming a bond with the other electron that came from hydrogen. And somewhere in solution, we have another bromine radical, which will continue the reaction by attacking yet another alkene, yet another alkene, and yet another alkene. Once again, a propagation step and no termination. Look at that. Initiation, propagation, 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 and it will continue with propagation until all the molecules are used up. Question: how do they differ from other types of reaction mechanisms in organic chemistry, such as nucleophilic substitution or electrophilic addition? In this case specifically, because we're adding HBr, this is an addition reaction, but this is a radical halogenation. The addition happens with a radical mechanism, whereas the dark reaction is an electrophilic addition. The way that you know the difference when you look at the mechanism is in terms of how it's initiated. We have the peroxides which form a radical, and the fact that you have radicals going throughout. In the dark reaction, you don't have enough energy through heat or light or something unstable to form that radical. And that's where you have to do the double-headed arrow so that you can show a carbocation for a completely different type of mechanism. So I hope that answers your question. And in this case, we're going from an alkene, yes, in both cases, an alkene to a halogenated alkane. The carbocation intermediate gives me a Markovnikov addition. The radical intermediate gives me an anti-Markovnikov product. All right, so that is alkene halogenation. And one more reaction that I was asked to cover is allylic halogenation. And specifically, we're going to focus on allylic bromination, but I'll show you both. One of my students, this is a tutoring client from a couple of weeks ago, she had a test question that looked like this. Orgo 2 students, I want you to see if you can come up with the solution where the product looked like this. And she had to show this step-by-step mechanism. Now, if you watch my Diels-Alder videos, you'll recognize that anytime you have a ring with a pi bond where you started with something that was smaller, that was a Diels-Alder reaction. In a Diels-Alder reaction, we have a diene and a dienophile, where if we break it here, our diene should have been a molecule that looked like this, and then this was the dienophile, which is all nice and well, but the professor gave them the wrong molecule, or so they thought. The key with this reaction was recognizing, and this a lot of students didn't get this right, The key was recognizing that they had to turn this molecule into this molecule. And the way you would do that is by first adding a halogen. So you have an intermediate that looks like this. And then eliminating it somehow, moving the pi bond to get this. How do you get a halogen onto the carbon next to a pi bond rather than actually breaking the pi bond? Do you see the question? Do you understand the question that I'm asking? So again, let me show it to you. The reaction that I just finished showing you, I had a pi bond. I reacted it with HBr. Why am I showing this in such a light color? I reacted it with HBr under radical conditions. The pi bond broke, bromine added here, and hydrogen added here. If I try to do this with Br2, it's not going to do much better. It's still going to have, well, let's see. If I try to do this with Br2, the pi bond will break, and I'm going to get two bromines adding. So how do I get the bromine adding here? This is where you have to do a completely different reaction. If you do this under very, very, very high temperature, then instead of breaking the pi bond, you're going to get the halogen adding here. And when I say very high temperature, I looked it up and it's 350 degrees Celsius. That is so, so high that if you're trying to do this in a reaction in lab, then first of all, it's not very safe. And second of all, if the temperature is not super high the whole time, or it starts to go down, or whatever is going on, if your temperature is not perfect, you're going to get a mix of products. And that is no good. So what we need is something that will allow the reaction to proceed as directed here, the way we want it to go, without having to raise the temperature that high. What can we do instead of raising the temperature to make sure the halogen goes where we want it to? That is where we bring in another molecule, and that is called NBS. For some students, it's enough just to know that the molecule is called NBS, but some of your professors actually want you to know what it looks like. And that specifically is this right here. You'll see it with radical halogenation, and you'll also see it with a Gabriel synthesis much, much later. NBS stands for N-bromosuccinimide. There are two C's somewhere. Let's see, succinimide. Pretty sure I spelled that correctly. N-bromo, bromine on N, succinimide is this molecule right here. If you don't have to know the name, here's what I do want you to know from N-bromosuccinimide. I call it a radical babysitter. It babysits the radical and makes sure that the radical does not get into too much trouble and only does the reaction it's supposed to do and nothing else. Now, this reaction, it starts out with just a hydrogen. You react it with HBr. That's how you form this right here. And that will also give us a little bit of Br2 in solution, which we'll see in the mechanism. So I want you to understand that this is going to cause some Br2 to form, which is very important for what we need. So let's go. I'm just going to copy this because I don't want to draw it again. And let's take a look at the mechanism to see what happens here. If I have an alkene that looks like this, and I react it with NBS, with a little bit of heat, some radiation to get the reaction to form, here is what is going to happen. The first step, this is the new step, is where the NBS is going to be zapped and cause this to break apart. This right here is going to give me an intermediate nitrogen radical. Don't care about it. But what I do care about is the fact that I just formed a bromine radical without having to raise the temperature to 350 degrees and without having to do anything too crazy. This bromine radical, in the presence of NBS in this situation, is going to then attack my alkene in a very similar mechanism to what we saw before. Bromine is going to attack not the pi bond, it's going to attack the hydrogen nearby. The hydrogen closest to the pi bond is the most susceptible, the most reactive, and that's here. We'll show that attack, single-headed arrow. Hydrogen is forced to donate an electron, and this electron collapses onto the carbon chain. As a result, I get my radical here next to the pi bond, which we'll show in dark blue. And then off somewhere in solution, I have an H and I have a Br. So I have HBr, which is going to react with another of the succinimide molecules to form more NBS to keep this reaction going. But this is what we want to focus on. Because the radical forming over here means that if you're trying to predict the product, we said the radical is forming in this position, you would expect the final product to look something like this with a bromine here. And you would be absolutely correct. But surprise, you're going to have another product. And your second product is going to look something like this. How on earth did that happen? What do you think? Question. Where can I find your videos of curved arrows to indicate movement of electrons? I actually have a couple of them linked under this video. So I have the radical resonance and a couple more that you can find. And if there's another video you're looking for, they're also on my YouTube channel. What happens to give us the second one is that when we have that radical intermediate, we have one option where this reacts as it is. But the second option is resonance. These electrons will resonate, these electrons will resonate, and what color did we not use yet? We'll use light blue. These will collapse here. The resonance structure is going to look something like this, where now I have the pi bond between the red electron, the green electron, like this, a radical formed over here, and now, remember I told you that there's some Br2 in solution? Option 1 is a Br2 molecule getting attacked by this radical. And option 2 is a Br2 radical getting attacked by this molecule. And both situations will have the same exact mechanism. Donate, break, donate, break. And so my products, as I already showed you, but I want to show you here with the colors so you can see exactly where they came from. On the left, we have a bond to bromine with the blue electrons. On the right, we have the bond to bromine with this one right here, which is a dark blue electron. And now let's account for everything else. We showed this one in red, this one in, wait, hold on. What am I showing? Oh, I showed you the resonance, but if we're showing the product here, then you have to ignore the resonance and just look at this big arrow because that's the one giving me the product. And that means this pi bond hasn't been touched. So let me show you the colors that I had it in. The pi bond hasn't been touched. That means the blue electron hasn't resonated. The red electron hasn't resonated. And that's my first product. For the one on the left, I have the pi bond that formed here between the green and the red. And then the blue one is the one that attacked bromine. In each case, we also have a bromine radical off in solution, which is just going to continue propagating this reaction. question. To form the more stable alkene. Yes. So what you're looking at here in terms of major and minor, given enough energy for this system to go into the most stable product. So ideally you put enough energy in the system, it only wants to form, well, it prefers to form the most stable product because that's the lowest energy product. This one right here has a more substituted pi bond, which means this one is a more stable product. You don't look at where the bromine is when determining the stability. You look at the pi bond. This one is less stable. And so even though this is what looks like it would be the product, this is also another option. Now we just went through a lot of radical concepts and quite a few different mechanisms for radical reactions. Your next step to make sure that you get this, to make sure that you understand, is to do additional practice problems. And that's why I created a practice worksheet for this session. So go to leah4sci.com/orgoalive and you'll get a link to the recording, the session notes, and the practice worksheet where you have quite a few mechanisms and reactions to work through. Now, all of this is just one topic in organic chemistry. And if you found this helpful, and if you found this style of learning, this beginner, let's learn and understand the topic, and you want to learn more advanced topics, not just more advanced topics, if you want to go more advanced into each topic, such as radicals and everything in Orga 1 and 2, then I want you to come join me in the Organic Chemistry Study Hall. Because what I have on YouTube are just my beginner concepts. I take a topic, I dig into it, I make sure that it's explained so that you can understand. But in the study hall, I take each chapter to the next level with more advanced practice, more tricky, look out for this, look out for that, and a lot more practice. And you can join my members only tutoring and support group where you can post daily questions so you get help with your homework, with concepts you don't understand. And of course, anything on the worksheet for this session or any other worksheet that I have posted. If you have questions, if you want me to show you how to do it, I cover all of that in the study hall. The link to sign up is leah4sci.com/join. And as soon as you sign up, you can jump right into the group and start asking your questions. Again, the link is leah4sci.com/join, and I hope to see you there. Have a wonderful evening, and I'll stick around in the chat for another minute or so to answer questions before it cuts me off. And so whatever questions you have, just go ahead and quickly type them in. Have a wonderful evening.